Hello everyone. In this video, I will discuss about parallel processing with OpenMP. My name is Madhav Gupta. I am currently studying in Bennett University. I have made this video for my assignment of course High Performance Computing. So let's start with the introduction. So what type of machines do we have now? Uh, we have types of parallel machines that are distributed memory machines and shared memory. What is distributed memory? Each processor has its own memory address space. Variable values are independent. If x equals to 2 on one processor, then x equals to 3 will be taken in on a different processor. Examples of this distributed memory are Linux clusters, Blue Gene. Next is shared memory. Shared memory is also called symmetric multiprocessing, that is SMP. Single address space for all processors. If one processor sets x equals to 2, x will also equal to 2 in other processors unless specified otherwise. If it is specified uh, otherwise that in one processor it is x equals to 2 and in another processor it is given x is not equals to 2, then that can be another case. Examples of shared memory are IBM P-series, SGI, Altics. So this is the diagram showing difference between shared versus distributed memory. In distributed memory and every different processor utilizes different memories, and in shared memory every processor shares one memory. Multiple processes. Each processor typically performs independent tasks. Multiple threads. A process spawns additional task threads with same memory address space. Now we should understand what is OpenMP. We have understood why there is need of using OpenMP to make task work on different processors. That is parallelly we have to run the programs. OpenMP is an application programming interface, that is API, for multi-threaded parallelization consisting of source code directives, functions, and environment variables. We will also see what are the functions in this video further. What are the advantages of OpenMP? OpenMP is easy to use. It is used for incremental parallelization. It is flexible at loop level or coarse grain. It is portable since there's a standard will work on any SNP machine. Now the disadvantage of OpenMP is only that it can only be used on shared memory systems only, not the distributed memory systems as we discussed in previous slides. Let's start with some basics of OpenMP. Basics. Goal: distribute work among threads. Two methods will be discussed here to distribute the work among threads. At loop level, specified loops are parallelized. This is approach taken by automatic parallelization tools. At parallel regions, sometimes called coarse-grained, don't know good way to start argument with precise people, usually used in message passing (MPI). This is the diagram shown for the loop level and for the parallel regions. This is the diagram. In this loop level, it goes serial-wise. The first state will come, then second, then third. And in parallel, all the tasks are performing parallelly. Parallel do and parallel do, this is Fortran, and parallel for C directives parallelize subsequent loop. This is how we start this parallel do in our code. OMP parallel do. This is our algorithm for some code. We have to use this dollar sign here for fixed format for trend. This we write this pragma omp parallel for when we start the parallel execution of our code. This is given an example. Suppose max I is equals to 1000. Thread 0 gets I, that is from 1 to 250. Thread 1 gets I to 251 to 500. And further we can extend this to thread 2, that's 501 to 750. The barrier is implied at end of loop. Work share for Fortran 90/95 array syntax. The parallel work share directive is analogous to parallel do. Previous example would be um, we start this by writing dollar $OMP parallel work share our algo, and that is here A equals to B plus C. Then OMP and parallel work share also works for all and where syntax. What is now shared versus private? In parallel region, default behavior is that all variables are shared except loop index. All threads read and write the same memory location for each variable. This is okay if threads are accessing different elements of an array. Problem if threads write same scalar or array element. Loop index is private, so each thread has their own copy. Here is an example where a shared variable I2 could cause a problem. So you can look at this example to understand this concept of shared versus private, where I first is given 10 to I equals to 1, I max, I2 is given as 2 multiplied by I, and ji goes to I first plus I2. Now in second one, the I first equals to 10. Now for loop, I is less than this, and I2 equals to this. Ji equals to I first plus I2. OpenMP clauses modify the behavior of directives. Private clause creates separate memory location specified variable for each thread. This is a question for parallel execution of the previous example we saw in our last slide. Look at memory just before and after parallel do or parallel for statements. Let's look at two threads. This is before, and when we add an additional thread, this is our state. Both threads access the same shared value of I first. They have their own private copies of I2. The thread 0 will also access I first from here, and this from also access the I first from here, but they will have their different copies themselves. Now Let's look what are the data dependencies. Data on one thread can be dependent on data on another thread. This can result in wrong answers. Thread 0 may require a variable that is calculated on thread 1. Answer depends on timing. When thread 0 does the calculation, has thread 1 calculated its value yet? Example: Fibonacci series, Fibonacci sequence. So what is first? Let's look what is Fibonacci sequence. This 0, 1, 1, 2, 3, 5, 8, 13. We can see every element of Fibonacci sequence is sum of previous two elements. Let's look at it. 13. 13 is sum of 5 plus 8. Now the algorithm for this Fibonacci sequence is given below. We have initialized the first element as 0 and second element as 1, and let's start our loop from third element, and we write the third element as the initial element and the second element. Now we can end our loop here. We have to parallelize this loop for on two threads. Thread 0 gets I equals to 3 to 51. Thread 1 gets I equals to 52 to 100. Now look carefully at calculation for I equals to 52 on thread 1. What will be the values for I minus 1 and I minus 2? A test for dependency. If serial loop is executed in reverse order, will it give the same result? If so, it's okay. You can test this on your serial code. What about subprogram calls? This is the subprogram calls when we call a different function in our loop. Does the subprogram write X or Y to memory? If so, they need to be private. Variables local to subprogram are local to each thread. Be careful with global variables. Let's see some more basics, more clauses. We will look at more clauses. Can make private default rather than shared. Fortran only, handy if most of the variables are private. Can use continuation characters for long lines. Can use default none. Declare all variables except loop variables as shared or private. If you don't declare any variables, you get a handy list of all variables in loop. You can look at this code and understand about these clauses yourself. First, private. Suppose we need a running index total for each index value on each thread. If hyper were declared private, the initial value would not be carried into the thread. Solution of first private clause creates private memory location for each thread, copies value from master thread 0 to each memory location, saves value corresponding to the last loop index, last in the serial sense. Now the reduction problem. Following example won't parallelize correctly with parallel do or parallel for. Different threads may try to write to someone simultaneously. Someone is initialized by 0.0. Do I equals to 1 max I, someone equals to someone plus AI. We can see that two different threads are trying to uh, change the value of someone simultaneously. Solution. Reduction clause. We can use the reduction clause to overcome this situation. We can use reduction clause like this, as you can see in the slide. Each thread performs its own reduction. Sum, in this case, results from all threads are automatically reduced, summed at the end of the loop. Fortran operators, intrinsics, max, min, I and IEOR plus multiplication minus etc. C operators plus multiplication minus division etc. Round of error may be different than serial case. Num threads. Number of threads for subsequent loop can be specified with num threads clause. N is number of threads. Conditional compilation. Fortran: if compiled without OpenMP, directives are treated as comments. Great for portability. Dollar $! Can be used for conditional compilation for any source lines. C or C++ conditional compilation can be performed with the _OpenMP macro name. Let's see some basic OpenMP functions. OpenMP get thread num returns the ID of current thread. OpenMP set num threads nth threads. Subroutine in Fortran sets number of threads in next parallel region to n threads. Alternative to OMP num threads environment variable overrides OMP num threads. OpenMP get num threads returns number of threads. Thank you everyone. That's all for today's video. I hope you all like it. I will also share my blog link in the description below on this topic. You can refer to the link for some tutorial on OpenMP. Thank you everyone.